First of all, you've been asked, if you've got this equation, which one of these others without any fractions or decimals in the exponent is it equal to? Well, remember to use your calculator. You could graph y equals 50 times e to the negative 0.693t, and you could graph y equals 50 times 0.5 to the t, or 50 times 0.75 to the t, or 50 times 1.15 to the t. And if I recall, this matches this. So that's one way to approach a problem like that. The next part of the problem stems from the idea that when you have exponential growth at some rate, your final value will be your initial value times 1 plus or minus your rate to the t. And so as we look at all of these, what kind of rate would end up with a base of 0.5? Well, 1 plus or minus r would have to equal 0.5. Therefore, r must equal negative 0.5. So we are decaying at 50%. So for this one, if we have 0.75, we are decaying at 25%, or 0.25, because 1 minus 0.25 equals 0.75. Similarly, a 15% growth would look like this. So we have decaying at 25% goes here, decaying at 50% goes to the top one, and there isn't one that represents this. Algebraically, you could also look at solving for the value of k. There should be a t here for these. If we looked at 50 times 0.5 to the t, that must be equal to 50 times e to the kt. And you could algebraically solve for the value of k. It's not the simplest thing to do, but you can do it. 50's on both sides, so those cancel through, and you have 0.5 t equals e to the kt. Well, taking the natural log of both sides allows us to bring the exponents down. And we have t times ln of 0.5 equals kt times ln of e. But we know that ln of e is 1, so we could divide everything by t. There should be a t here too, not a 2, but a t. Dividing by t, the t's cancel, and k equals ln of 0.5. So in all of these cases, if we look at natural log of 0.5, natural log of 0.75, natural log of 1.15, these in all cases should give us the k value. And it's easy to see which of these match with which of these.